Okay, welcome back to all the students. I'm starting with the second part of the optimization theory, and in this part, I'm going to discuss about the convex optimization problem, and then I will talk about how to solve such kind of an optimization problem. Okay, so let's get started. So, how can we write a sample optimization problem of a very general optimization problem can be written in this form. So you want to minimize f of x. I said in the last time you can also maximize f of x, or this is also equivalent to maximizing minus of fx. And then you have some constraints, subject to some constraints. For example, let's take fi of x is less than equal to 0. There are, let's say, m such inequality constraints and p such equality constraints. Okay, hi of x is equal to 0, and let's say these all are vectors. Okay, so x is a vector with dimension n. Okay, now then in the last class we also discussed that this optimization problem could be divided into many parts. For example, it could be a linear optimization problem, or it could be a non-linear optimization problem. Okay, so in non-linear optimization problem, in linear optimization problem, fx and all the constraints, they are all linear. While in non-linear optimization problem, one or multiple of them are non-linear. Okay, and a special case of non-linear optimization problem is called as a convex optimization problem. Okay, so we are going to discuss the convex optimization problem. This is our uh, interest here in this lecture. Now the question is, why do we want to look at the convex optimization problems only? The reason is simple. See, as I showed you in the last class, you can take a sample function which could be something like this. Okay, so this is your x and this is your f of x. Now where all it achieves, so you want to minimize f of x. So where all it is going to achieve the minima, it is here and it is here. Now suppose if you solve this optimization problem, you're going to get two values, 2 points, right? Now it is difficult for you to understand which one of these is a global optimal point. Okay, so I also talked about local optimal and global optimal. So you can get many points. I just showed you a sample example where there are two minimas here, but you can get multiple points. You can get multiple local points. For example, if you put a gradient equal to 0, you're also going to get this point and you are going to get this point also. So for any general function, you're going to get multiple points and it will be very difficult for you to say which one is a global optimal point. Okay, so let me write it down. This is an important point here. For a general problem, general function, let's say, you may get multiple optimal points, but it is difficult to say which one is a global optima. Okay, now it turns out that for some special class of functions, it turns out that you are going to get just 1 point as your point of interest or a critical point, and which you can say to be a global optima point. Okay, So for some special cases you get just one point, and which you can say to be a global optima point. And one such class of functions is, you can write it to be convex functions, or in other words you can write it to be a convex optimization problem. Okay, so this is the precise reason why we want to look at convex optimization problem, because when you solve a convex optimization problem, whatever point you are going to get, you can with guarantee say that it is a global optimal point. Okay, so this is the beauty of convex optimization problem. Now let's go back again and see what kind of problems are convex optimization problems. Okay, so again I'm writing the same thing: minimize f of x subject to the constraints that fi of x is less than equal to 0 for I goes from 1 to m, and hi of x is equal to 0 for I goes from 1 to p. And your x are all vectors, so x is x1 x2 till x. Now such kind of an optimization problem is said to be CVX. I'm writing in a short form, CVX, or a convex optimization problem. Okay, let me write it like this: convex optimization problem if fx and fix are convex functions and hix are linear functions. There is another way of writing linear functions. It is also called as affine functions. Okay, so in this you very well know what are the linear functions. Linear functions are of the form, you can write it as hi of x. It could be, let's say, ax plus b. This is a affine function, right? Okay, so this is in a single variable. If you have multiple variables, let's say, then you can write a1 x1 plus a2 x2 plus a3 x3 and so on plus b. So these two are affine functions. This is an example of a affine function where it is a linear function in x. Okay, now what are convex functions? You all know convex function. The definition of convex function is that a function is convex if f of alpha x plus beta y is less than equal to alpha times f of x plus beta times f of y, where alpha plus beta is equal to 1. Okay, so this is the proper definition of a convex function. The same thing you can put it for linear functions also. For a linear function, it is f of alpha x plus beta y is equal to alpha times f of x plus beta times f of y. So this is for a linear function, and this is for a convex function. Now graphically, what does it mean? So graphically, if I plot, if a function has some shape which is of this kind, this is your f, this is the x, this is your f of x. If a function is of this kind, so if you take 2 points here, this is, let's say, x, this is y. So if you join the line between the two, so any point if you take, so this point you can write it to be alpha x plus 1 minus alpha times y. Okay, alpha lies between 0 and 1. So if you take any point here, so this point is what? This point is this value here is going to be f of x, this value is going to be f of y. So this point here is going to have the value alpha times fx plus 1 minus alpha times fy. Okay, and so this is the interpolated point, which is here, this value. Okay, this value is here. And what is the actual function value at this point? So this point here is this, and the value of the function at this point, so let me write it to be f of alpha x plus 1 minus alpha y. So the thing here is that if you join 2 points on a curve, then the midpoint should always be above the function curve. Okay, so this is one definition. So if you are given any function and if you want to prove the convexity of that function, then you have to use this formula. So this formula is very important here. Okay, so this is how you are going to prove that a function is convex. Now many times this is a tricky business. Proving this is quite troublesome. So what we do is we have something called as a second order condition. And the second order condition for convexity is that, as you know, if you take the double derivative of a function with respect to x, and if it is greater than 0 or greater than equal to 0, then you say that the function is convex. Okay, so this you do in a single, if x is a kind of just has one element or a scalar, if x is a scalar, then you can use this formula. You find out the double derivative. If it is greater than 0, then you say the function to be convex. Now the definition slightly changes in the case of if x is a vector, then you need to find out the Hessian, and Hessian is written something like this. Now you have to put this Hessian, you have to prove if it is greater than equal to 0. What does it mean? It means positive semi-definite. Okay, so this we discussed in one of the earlier lectures. So for a function, if it is a function of a vector, then you find out the Hessian. How do you write the Hessian of a function? So Hessian is given by del 2 fx over del x1 square, del 2 fx over del x1 del x2, del 2 fx over del x1 del x3, and so on. Similarly, in the second row, you have del 2 fx over del x1 del x2, del 2 fx over del x2 square, and so on. Okay, so this will be your n cross n matrix. So this is a matrix. Okay, so this is a matrix of order n cross n. Now what do you mean by a matrix being greater than equal to 0? It means that a matrix, so I'm writing here as PSD, this is in short form, you can write as PSD. A matrix is positive semi-definite if for all any vector you take x not equal to 0, x transpose AX is always greater than equal to 0. Okay, so this is a definition of a matrix being positive semi-definite. So what you need to do is you have to take all vectors x which belongs to Rn, okay, in the real plane, n-dimensional real plane. If you take all of the vectors in x and if you do this multiplication, x transpose AX, and if it is greater than equal to 0 for all x, then the matrix is called as positive semi-definite matrix. Okay, Now there is another way of proving a matrix to be positive semi-definite, and there are a few shortcuts to prove a particular function or a particular matrix to be positive semi-definite, and that is, so I'll talk about three methods here. So the first method to prove a matrix to be positive semi-definite, method 1 is, if you convert, so first step here is to convert the matrix in row echelon form. So in this matrix, if a matrix is in row echelon form, then if all the pivots in the matrix are greater than equal to 0, then we can say the matrix is PSD. Okay, then we can say matrix is PSD. Now what do we mean? How a row echelon form looks like? So if you have a matrix, let's say if a matrix is something like this: 2, 1, minus 3, 5, minus 1, 0, 0, 0, minus 4. Okay, so you can see these components I've made it 0 by making row and column operations on a matrix. So this is called as a row echelon form. Okay, so you know how to make a matrix to a row echelon form. So these are the pivots. So first non-zero element of a row is called as pivot. Pivot is what? Let me write it. Pivot is first non-zero element in a row. So if these pivots are all positive, then you can say matrix A to be positive semi-definite matrix. So here you can see this pivot is negative, so this is not a positive semi-definite matrix. So this is not a PSD. You can take another example. Let's take another example. If it is something like this. Now here you can see these are the pivots here and these are all positive. So this is a positive semi-definite matrix. Okay. So there's one way of proving that a matrix is positive semi-definite. Okay, there is another method, method 2, let me write it. Method 2 is, if you take the determinants of all upper left sub matrices, and if the determinants are positive, then you can say the matrix to be positive semi-definite. Let me illustrate that. So let me write it first. Determinant of all upper left sub matrices are greater than equal to 0, then the matrix is PSD. So let me take an example. Let's say A is given to you something like this: 2, minus 1, 0, minus 1, 2, minus 1, and this is 0, minus 1, 2. Okay, you please remember that this particular matrix here, the Hessian matrix, this is always symmetric. Okay, this is always symmetric. You can see these two components are same. Okay, and so on. So if you take this matrix, so what is the determinant of all upper left sub matrices? So the first upper left matrix is 2. So this one is the first upper left matrix. This is the second upper left matrix, and this whole is the third upper left matrix. So if you take first one, so determinant of this is 2. If you take the second one, which is something like this, then this determinant is how much? 3. And if you take the determinant of whole of this matrix, and if you compute the determinant of this, it turns out to be 4. So all these values are greater than equal to 0, hence the matrix is PSD. Okay, So in this, if you are given a matrix, what you do is you find out the determinant of all the upper left submatrices and prove it greater than equal to 0. Now what about the third method? Third method is also very simple. If eigenvalues, if all eigenvalues of a matrix is greater than equal to 0, then the matrix is PS. Okay, so these are the three methods that I have told you to prove how to prove a matrix to be PSD. Okay, so if a matrix is PSD, then you can see here, you can say that the function is convex. Okay, so if your Hessian is positive semi-definite, then you can say your function to be convex. So now what is a convex optimization problem? Again, we go back to our original definition. A convex optimization problem is a problem where your function and the inequality constraints are convex functions and your equality constraints are linear functions. Okay, so this is the definition of a convex optimization problem. Okay, now how do we solve such kind of an optimization problem? Um, So to solve such kind of an optimization problem, we form something called as a Lagrange dual function. Okay, how to solve how to solve such convex optimization problem. So I'm again writing the function minimize f of x subject to the constraints that fi of x is less than equal to 0. There are m such I constraints, and then hi of x equals to 0. There are p such constraints, and x is a vector. Sorry, x is x1, x2 till x. Now, how to solve it? You form a Lagrange function. So what we do is we form a Lagrange function. I'm not going into the details of why do we form a Lagrange function and how it solves it. I'm just going to give you the crux, okay, the final results, and you can directly apply it to any problem, any convex optimization problem, and it is going to solve for you. So for a Lagrange function, you have your Lagrange function is a function of x, which is called as a primal variable, and this is also called as a primal problem. Okay, primal or primary problem, you can say. So Lagrange is a function of x, the primal variable. So this x is called as primal variable, and then it is also a function of lambda and nu, which is called as dual variables. So lambda and nu are dual variables. So we form this as follows. We do this fx plus summation I goes from 1 to m lambda I fi of x plus summation I goes from 1 to p mu I hi of x. So this is what we form a Lagrangian. We call it as a Lagrangian. Okay. And what we do is, how do we solve it is that we form something called as a KKT conditions. Okay. So we form something called as a KKT optimality conditions. So this is called as Karush-Kuhn Tucker conditions. In short form, you write KKT conditions. Okay, and it says that so there are a list of conditions here. So at the optimal point, So at optimal point x star, your Fix should be less than equal to 0. This is from the constraints. Okay, so constraint should meet. Again, the other constraint should be equal to 0. Again, the constraint should meet. Then it says an interesting thing. First thing is that the lambda is at x star. Okay, sorry, the lambda is the first dual variable which is with the inequality constraints here. This should be greater than equal to 0 for all i's going from 1 to m. So all the lambda i's which are associated with the inequality constraints, these should be greater than equal to 0. The other condition here is lambda I times fi of x star. This should be equal to 0 for all i's going from 1 to m. And the last condition is gradient of f at x star plus summation lambda I star gradient of fi at x star plus summation mu I star gradient of hi at x star. This should be equal to 0. Okay, so these are the 5 KKT conditions. The first two are the inequality conditions. The third one says that your Lagrange dual variables associated with the inequality constraints should be greater than equal to 0. The fourth one is also called as the complementary slackness theorem. Let me write it to be complementary slackness theorem, which says that the product of lambda star times the Fix star, it should be equal to 0. And this is the fifth condition, which says the gradient of the Lagrangian, if you take the Lagrangian here, the gradient of the Lagrangian with respect to x should be equal to 0. So this is with respect to x. Okay, so this sums up how to solve a convex optimization problem. Let me revise it once more. A convex optimization problem is one where your fx and fi of x, these are convex, and your hi of x is a linear function. So how to solve it is that at an optimal point x star, your constraints should satisfy. Then your Lagrange dual variables associated with the inequality constraints should be greater than equal to 0 or positive. And the product of the Lagrange dual variable and the inequality constraint function should be equal to 0. And the gradient of your Lagrange with respect to x should be equal to 0. Okay, so this is the way of solving a convex optimization problem.